All right, what's up, everybody? We are live and running. Thank you for those tuning in and joining us. I know it always takes a few seconds, maybe minutes, for people to realize we are live. But Cody, I like that house you're in over there.
Yeah, I bought it just a couple minutes ago. It's not a blur screen at all.
Can't tell at all. We're in the midst of maybe moving. Probably the worst time to do that, but I think we put an offer on that house behind you.
Nice.
Same
Yeah.
house.
We might end up, and living in the same house soon. You never know.
Awesome. Well, we're excited. We try to do these live workshops, live problem solving workshops as often as we can. And we love hearing from you. So if you have problems that you're struggling with, either FE or PE related, please submit them to us. You can email me at isaac@civilengineeringacademy.com, and we kind of get them in queue so we can do some live problem solving sessions. Now, the beauty of having Cody on is he is in the midst of studying for his PE. So you're going to get some good stuff as he's going through this stuff the same time as you are. So anyway, that's a quick introduction. If you need additional help, please don't hesitate to check us out, civilengineeringacademy.com. We do have full-blown courses for you. We also have a ton of practice problems right here on our YouTube channel or wherever you're finding us. But YouTube, we have a bunch of problems there for free and other stuff too. Check our podcast out too. I will be manning the chat room and hopefully answering questions there. If you have additional questions, I'll chime in and stop Cody, and we can get to your get those answered. And yeah, that's I think all I got for a little housekeeping. Speaking of that beautiful house. So, all right, Cody, I'm going to turn the time over to you. Let's jump into our problems. We'll go full screen mode here.
All right. Well, a couple housekeeping things on my end. The last live I was in, we had issues with the Wi-Fi. We're hoping that that's solved since then. But if it isn't, if something acts up, I promise you I'm going to do my best to hop back in, 30 seconds later or something like that. We had an incident a little bit earlier. So I think I've got it fixed, but just in case, we'll try. Well, I'll be back, I guess is what I'm saying, if something happens. Also, last time I didn't have the chat room open, so there may have been something that kind of went through the cracks. But I've got it open now. I've got it thrown up on my other screen, so hopefully we'll be able to read those just in case one gets missed. So this is the first problem that we've got here. This is going to be a traffic engineering problem. I'm going to be taking the transportation depth exam. I know I haven't had the guts to take it yet. I'm probably going to take it in November, probably mid-November. I'm kind of in the heat of studying. So anytime that you guys email Isaac with questions, it helps me too, because whenever you send in questions, it'll help me refresh on that topic. So hopefully that kind of makes sense. We're helping each other basically. So, and I'll make a video off of it. So, all right. So this one is a traffic engineering problem. We're going to be talking about some traffic analysis. Here's what the question says. Given the following speed data, determine the mean speed in miles per hour. Now, this problem is a little bit simpler than it may seem. Whenever I saw this problem starting out, I was a little bit confused and kind of worked through it, and it started making sense. So the first step to this guy is finding a formula, and this is going to be a PE. This is going to be a PE reference handbook problem. You probably won't see this on the FE, but it'll be on the PE for sure. So we're going to have version 1.2. That's the latest and greatest at the time of this recording. And we need to make sure that we're looking in section. I'm just going to write SEC 5.1.2.5. All right. And that's going to be on page 274 of the PE reference handbook. All right. And when you go there, you're going to find a formula that looks a little bit like this. It's going to be mean speed is equal to sigma. That's the sigma. I think it's Greek symbol sigma. We're going to have a lowercase n with a sub I, and then we're going to have a capital S with a sub I. I'll explain what all these are here in a minute. And then we have a capital N in the denominator. All right. So to talk about some variables here, obviously this X bar, this is your mean speed. So I'm going to try to write neatly. I have terrible handwriting, but all right. So that's your mean speed. This guy right here is your frequency. So it's the number of vehicles in that speed group. All right. So hopefully that makes sense. So it's your frequency. The capital S is your average speed. So we're given speed groups. What we need to do is solve for an average speed out of those speed groups. Okay, and I'll kind of walk through that. This in here is the total number of vehicles in our study. So that's just adding the frequencies up, and we end up with a number. So I'm going to go ahead and get started here. So our S, I don't know if I have room. Let me see. We're going to try it. Capital S right here. Okay, y'all can see that. I'm going to write a capital S right there, right next to that 46 through 50. And what we're going to do is we're going to find the average of that speed group. This guy right here is 48. We have 53 on this next one. Let's see, 58. And then I think it's 63, 68, and so on. This is the part where I'd kind of, on a video, I would pause it and edit it out because it's kind of boring just watching me write. That's 78, and this is 83. Okay. So basically what I did is I did 46 plus 50, divide that by 2, you get 48. 51 plus 55 divided by 2, you get 53. That's your average in your speed group. You're assuming that 5 vehicles are going 48 miles per hour. That's really the only way that we're going to be able to solve this is by finding an average out of that speed group. Hopefully that makes sense. All right. So this guy right here, I'm going to go ahead and write down here. We got a mess of an equation. So we have 5 vehicles times our average speed, 48 miles per hour. Plus, this is going to be very repetitive here in a minute, 15 vehicles times 53 miles per hour. There we go. Plus, you see where we're going with this. This can get pretty boring pretty quick. 47 vehicles times 58 miles per hour. And always write out your units. I had a professor, let's see, I think it was my junior year of college. I had a professor who, if you didn't write out your units, he would dock you like 10 points, something stupid. And it really frustrated me because I didn't write out my units. But looking back, I'm pretty thankful that he did that. We have 56 vehicles. I'm going to have to double check and make sure this is all right too after I write this stuff out. I might be missing one. Plus 52 vehicles times 68 miles per hour plus, again, this is usually where I kind of skip in the YouTube videos, vehicles times 73 miles per hour plus 35 vehicles times 78. All right, let's see. And then I think we got one more here, 27 vehicles times 83. Did I miss one? Somebody tell me. Somebody tell me if I missed one. Let me check here. So we got 5, 15, 47, 56, 52, 42. I think we got them all. All right. We're going to put over the total number of vehicles. So you just add 5, 15, 47, 40, 56, 52, yada, yada, all the way down to 279 vehicles. All right. So basically what this is, let's think about this conceptually, right? What does this mean? What we just did essentially is basically create a weighted average of these speeds, mean speed, weighted average. Think about it that way. If you're working through like a water resources type of problem, you're going to be dealing with a lot of, curve numbers or let me think. I'm totally blanking, but a Q equals CIA rational method. A lot of C, the coefficients for the rational method. You'll be finding averages of those based on the areas, the acreage. It's the same thing basically right here. So instead, we're having vehicles and speeds. That's really it. So whenever we plug this into our FE/PE approved calculator, if you haven't already, go ahead and check. Make sure you have an FE or a PE approved calculator for your exam. I can't remember if they checked. I think they did. I think they checked whenever I took the FE, they actually checked the calculator. So make sure that you don't walk in with like a TI 84 plus and you end up with no calculator. All right, so when you solve for this guy, we have X bar equal to 67.61 vehicles. Also, something I want to bring up real quick. We have a mean speed, right? In miles per hour, it's saying given a determine the mean speed. Let's go ahead and round this dude up to D. That's where we are going to find our answer there. So this is going to be miles per hour. This is the average speed. Oops. My goodness, I keep erasing. That is the average speed among all of the vehicles given the frequencies and the speed group. So the answer is going to be D for this one. Is there any questions on this one? I saw the chat lighting up.
Let me go to the chat room. I think this one's pretty straightforward. I haven't had any questions related to the problem. I did
Everybody
post
good?
some questions. I was jumping in there asking stuff. Um, I think we're good. If you guys have any questions on this problem, though, please feel free to post it, and we will go back to it.
Yeah, and there's no stupid question, by the way, with these. And also, whenever I move on to the next problem, if you have a question about problem one while I'm on 2, 3, or 4, we can hop back. Super easy. So no worries on that. With
Aiden got the same answer, so you're
good.
good.
That there's an issue always if there's not. That's good. That means I did it right. All right. This next one I think is pretty unique. This is something that you could see on the FE or the PE. The FE, they don't really give you a lot of material on it. So it's kind of maybe they won't ask you for the bearing, but they'll ask you like what quadrant it would be in, something like that. But for the PE, I'm studying the PE. This was kind of something that a similar problem popped up, and I figured this is a good workshop problem. So we're going to work through it. I'll kind of give you a little bit of bonus info too while we're working through it. So this is going to be a surveying problem or a basic math, as I like to call it. I don't think there's a section on it, but it would be a breadth problem for sure. You won't find this on your depth stuff. So it says a surveyor has calculated an azimuth angle of 276.175 degrees. What is the bearing in degrees, minutes, and seconds? All right. It can get a little tricky, but let's just, if you think about this in a way of quadrants, you can solve this without even doing any math. But I'm going to go ahead and go through the problem and I'll explain to you how that's possible. I'm going to draw a picture. This is a good idea for whenever you're taking the exam and you see an azimuth problem. Go ahead and draw your quadrants or Cartesian plane, if you will. That's the word I was looking for. 0 with an azimuth starts on the north axis. So it starts up north and it works. Let me think here. Clockwise. It works clockwise. That's an azimuth. So we have 90 here, 180 down here, and then 270, I think it is, down here. All right. And so we're starting here at 0. We're going to go around the circle until we get to 276 degrees. I didn't have a protractor out for this. Oh, my goodness. Look at there. I didn't have a protractor for this one, so that might not be exact, but this is 276.175 degrees. And so now you can kind of see how you can, if you draw it out, you basically have the answer. You don't have to do any math. But it's good practice anyways. By the way, this is north, east, south, and west. So what is it? Never eat soggy waffles. If you forget that, that's a good way to remember the Cartesian plane there. So you can already see now from the north to the west, your some odd degrees. I mean, the answer is probably going to be A, but let me think here. B. B is probably going to be our answer, right? But we're going to go ahead and solve it. So what we need to do is we need to solve for sort of this angle. So the way bearings work is it pulls off of the major axis being north or south, but it's going to be the nearest axis. So think about this, right? Technically, let me think. No, I better not say that. I was going to say something, but it didn't. We're pulling from the north to the west. That's the closest sort of, let me think here, angle from a major plane. If you went from south, you can kind of see how you do more than 90 degrees. So you need to pull off of the nearest major axis, which would be north and south. You always start with north or south with your bearing, and then you work your way west or east. Okay. So if our line was somewhere like here, for example, let's assume that it's closer. Yeah, that'll work. So we'll pull from the south to the east. That would be our major plane, I guess, is what I'm looking for there, or pole. major pole there. So, all right. So, to solve for that, for this angle right here from the north to the west, we need to subtract 360 degrees because it's 360 degrees all the way around, right? So, all the way around the circle, you're talking 360 degrees. If we subtract that 276 from that 360, it will give us what we need from this north to the west. Okay. Does that make sense to everybody? I hope it does. So, we're going to subtract 360 degrees. We're going to subtract from it 276.175 degrees. So what you end up with is basically the answer. You're going to end up with 83.825 degrees. Now there's going to be a time. The reason why I included this, and it basically it's essentially an easy problem. You can solve it quickly within seconds if you know what coordinates you're dealing with. The reason why I included this is because you need to practice converting from decimal to degrees, minutes, seconds. There may be a problem on the exam where you have to solve for an angle and convert it to degrees, minutes, seconds, and they won't all be the same degree, minutes, seconds. So we could have had 83, 46, 29 or something like that instead of them all be the same. So there was two different avenues I could have taken, and I chose the easy route for the answers, but I wanted to show you guys how to do that. Now, there should be a something on your calculator. Let me see. I've got a TI 30X 2-bar S, whatever that is. And there's a way that you can convert 2 degrees, minutes, seconds. So I would definitely look into your calculator, see if you have that tool. If I'm going to write out the bearing in decimal form, we're going to have northing 83.825 degrees west. Okay, so that's the bearing, but we need it in degrees, minutes, seconds. And so what I look for in my calculators, there's the degree symbol, there's a second symbol, or sorry, minute symbol, and a second symbol. Whenever I click on that, you can also go to degree. Oops, let me redo that. Whenever I click on that, to degrees, minutes, seconds, that's what it looks like. So by doing that, what I do is I punch in 83.825 2 degrees, minutes, seconds, and it spits me out whatever the answer is, 83 degrees, 49 minutes, and 30 seconds. And then you just got to know the coordinates from that point, or the quadrant, rather. You need to know the quadrant that it's in. So there is your, it looks like that one's going to be B. Everybody good? Everybody doing good? Everybody still alive? Any questions?
Yeah, Jocelyn says from degrees to degree, minutes, seconds. Let me show this one. I just divide the number after the decimal by 60 and repeat. So that's the
That
way.
might, yeah, that might work. Yeah. Yeah, I didn't even think about doing it the hard way. Yeah, that's a good thought, Jocelyn. Thank you.
Yeah, there's a calculator way, or you can just divide these things by 60, and that'll slowly get your conversion. And she even posted
Nice.
the answer. Here you
Yeah,
go.
nice job.
Take 0.825 divided by 60, that equals 49.5. Take 0.5 divided by 60, you get 30. That is your degrees, minutes, and seconds.
I got to be honest, I forgot the long way a long time ago, and I'm glad she posted that because that's a good refresher. I didn't even remember that.
Thank you.
Everybody good? Any questions?
No questions on that one.
All right. Moving on. All right, we got a theory problem, everybody. I need some engagement out of the audience. Everybody's been pretty good so far, but this one I need some help with. All right. If you're taking the transportation depth, I think this would be right up your alley. You should probably know the answer to this one. This is going to be a traffic engineering, traffic analysis problem. It says, which of the following is not a characteristic? By the way, sometimes on the exam, they can underline not. They don't have to. So heads up, pay attention to the question. You can look right over that and circle the wrong one. Which of the following is not a characteristic of a basic freeway segment? Notice they didn't say a basic multi-lane highway. They said basic freeway segment. So out of the chat, I'm going to give everybody like 15 seconds. Kind of give me an answer, and we'll go from there. So I'm going to count down in my head and give everybody 15 seconds. And it's okay if you don't know it. I'll answer it. In the meantime, I'll talk about the course. So, Civil Engineering Academy has a really really cool course, and it's helped me a lot personally in the studies. They've got a breadth one and a depth course, and both of them have been really useful. I haven't dug too deep into the depth course yet for transportation, but the breadth one has really helped me brush up on a lot of skills. You can check that out at civilengineeringacademy.com. All right. So it looks like we don't have anybody hopping on, but the answer to this one is
We
going to
got an
be,
answer. We got an
oh, let's
answer.
go. All right, we're good. Whew. I was
Andrew's guess.
stressed.
Andrew's guessing B.
Okay, all right, okay.
Aiden's guessing, thinking B.
I was a little worried.
And
Everybody
Jerem's
was
guessing
asleep.
B.
I was
Yeah.
I was a little worried. I thought everybody had fallen asleep. Maybe they were watching some Sunday night football or something. Personally, I think this is way winning than any football game. Okay, I'll say that right now. I'm a Cowboys fan, so I've still got a little bit. All right, here we go. The answer to this one is B. Okay, a lot of you guys were correct. The answer to this one's B, and I'll explain it. Here's the solution that I wrote down, and then I'm going to go further into depth on why B is the answer. So the main difference, hang on, the main differences and characteristics between a freeway and a multi-lane highway is a divided median and a non-at-grade intersection. Typically, highways have a two-way left turn lane, a twiddle, if you will, is what I call it, twiddle, in lieu of a divided median, and they have at-grade intersections. So, where you can find the answer to this one, if you're taking the transportation depth exam, this is a good one that you need to look into. Highway Capacity Manual, chapter 12 of volume 2. So the way the highway capacity, I won't go into too into depth on this, but the Highway Capacity Manual is, I think, 4 volumes. Excuse me. First volume's more conceptual stuff. Second volume is uninterrupted flow. So basically, freeways, multi-lane highways. And by multi-lane highways, you can have stoplights on multi-lane highways, but they consider an uninterrupted flow anything that doesn't have a traffic signal within like 2 miles or something like that. I'll have to go back and look, but I think it's 2 miles. So that's uninterrupted flow. And then volume 3 is about interrupted flow, so traffic signals, that type of thing. And then volume 4 is something else. I can't remember what it is, but the main 2 guys that you're going to be in is volume 2 and 3 if you're taking the transportation depth. That's where you're going to find a lot of information about the basic freeway segment is in volume 2. Now, let's think about this, right? You have a posted speed limit between 50 miles per hour and 75 miles per hour. That's the typical speed for a basic freeway segment. In fact, I think I live in Arkansas, and a lot of our freeways are 70, 75 miles an hour. You won't really see a 75 mile per hour highway typically. Now, there may be more like in the 60, 65, but 75's up there. B, let me see if I can pull up Google Earth and maybe show you guys an example. Let's see. So we are talking, contains at-grade intersections, contains a divided median, or D, enters and exits only through interchanges. Man, look at there. All right, we got Google Earth pulled up, everybody. This is a good example of a freeway versus a highway. Here's your freeway right here. So you've got, let's see here, four lanes, I think. So there's, 3. I can't count. 3 and then 3. So this is a 6-lane freeway. The reason why I know it's a freeway is number 1, because it's got these little off ramps, right? And it has an overpass. And that's what it means by, what was it? At grade intersection. An at grade intersection would be something like this, where you have an intersection at grade, so that you're not going to have an overpass or some. A freeway has something similar to this, where you have an overpass and you have these on off ramps like this. All right, and I think freeways you can have anywhere from like 4 to 8 lanes, and a multi-lane highway is 4 to 6, I think. Here's your multi-lane highway over here. Here's your twiddle. So your 2-way left turn lane. So remember, this is not necessarily a median. It's a 2-way left turn lane. So if these guys need to turn left, they can hop in here and go that way, or vice versa. They can use this to get on. This guy has on-off ramps. And then it's got this median right here. This, you can't really see it, but this is a concrete barrier that separates the northbound traffic from the southbound traffic. So with that said, is there any questions about that? Does anybody have any additional questions while I've got the fancy Google Earth pulled up? Everybody good?
Go into the chat rooms. It looks like we just had our answer selections. Some are kind of all over the board with C's and D's, but nothing about.
Yeah, the reason why it's not C is because typically a freeway will have a divided median. It will. It is a characteristic of a basic freeway segment. Enters, exits only through interchanges, same thing. It is typically a freeway segment or a characteristic of a freeway segment. So that's why it's not C, D, or A. B is going to be your answer. And so the main difference between freeway and multi-lane highway, the next problem, is at-grade intersections and divided medians, right? So if you have an at-grade intersection and not a divided median, you're talking a multi-lane highway. If you are, yes, I did just see your chat. Yes, a highway would be, no, sorry, let me think. A highway is not D, it is a freeway. So a highway has at-grade intersections. So you hit a traffic light and you turn. Basically what I just had pulled up on the Google Earth. I thought you said freeway. That's why I got confused. Here's your highway, right? So you have a traffic signal right here. You can't, sorry. Let's see. Well, we can't do that. We have a traffic signal here, an at-grade intersection, and then we have a freeway here that has an overpass, right? So D, enters, exits only through interchanges. So think about like it entering the next facility. This guy, if they're traveling on a freeway, they have to enter / exit through this interchange. They have to hop on this ramp to take a left or a right. These guys right here, they don't have to do that. They just hit the traffic signal and they turn, or they go straight. So that's the difference between a multi-lane highway right here and a freeway. Everybody good? Is that still confusing? Did that clear that up? I appreciate the question.
Yeah, I think we're good.
All right. We're going to move on. If there's any further questions, we can hop back, but I'm going to go ahead and move on to the next question. So let's see here. Problem 4. All right. Here's another one. I need audience participation again. Don't be scared to be wrong. All right. Don't be scared to be wrong. Nobody knows you. This is going to be an FE or a PE problem. This is going to be something that you just need to know. I would lean more towards the PE type of thing.
Could I pause you?
Yes.
We have one question on the last one. No signals on a freeway? Question mark.
I haven't come across a signal on a freeway, so I would say you're correct on that.
Yep.
I would say that's a good question. I would say yeah, that's correct. Because it would be a uninterrupted flow. The freeway is. It's always uninterrupted. It doesn't have traffic signals or anything like that. But a highway, multi-lane highway, can be uninterrupted or interrupted depending on the frequencies of the signals. So if the signals are really close together, it's an interrupted flow type of analysis. So, all right, here's the question for the next one. Sorry, I got sidetracked, everybody. Which of the following admixtures provides relief from internal pressure as it pertains to concrete? So A is retarding, B is water reducing, C is air entrainment, and D is super plasticizer. Let's see what everybody's got here. Man, I'm seeing a lot of C's. I like it. Everybody's on board. I love it. I wrote down, it says air entrained air provides tiny air pockets of air within concrete where water can expand when it freezes. Air entrained concrete is recommended when a concrete structure is exposed to freezing conditions and is achieved by adding surfactants to a concrete mix. In other words, it almost creates a hydrophobic bond with water molecules. Think about freeze thaw and the cracking that happens from not allowing that concrete room to wiggle. This is part of the reason why bridges have those cross-sectional cuts / zigzags just at a much bigger scale. So let me see if I can find that on Google Earth, actually. I'm going to move over here. While we're chatting about that, anybody got any questions on that? I'm going to try and pull up sort of what I was talking about, those bridges. I I think I got it now.
Looks like everyone was guessing C or they knew C, so good job.
So here's kind of a good example of a bridge that kind of has that little break. This is to allow for expansion and contraction. My understanding, anyways. I'm not a structural engineer, but I believe this guy right here um, allows for expansion and contraction. It's not a very good picture. It's on Google Earth, but this allows the bridge to expand and contract with the temperature of what's going on around it. So good thought, everybody. Good stuff. That's part of the reason. Also, freestyle is part of the reason why you'll see like construction joints, contraction joints in like sidewalk. So if you're walking along sidewalk and you see some sort of epoxy along a joint, that is to allow for the concrete to wiggle whenever it freezes and thaws. Whenever it's really hot outside, concrete expands. Whenever it's like -20, obviously it's going to shrink, and that's how you get a lot of your cracking. And let's see. I'm looking over the chat. PCA, what is that? What is a PCA?
All right, one question from Jocelyn. Can we find the answer of this on the PCA?
It's a good question for you, Isaac. I have no idea. I don't know that one.
I think it's a standard, but I don't know the acronym there.
Oh, Portland Cement Association. I'm
Oh,
not
yeah.
sure. I would think so, but I'm not sure. This is just something that you need to kind of understand if you're taking the PE. It's one of those things where you should not. I don't know. It's kind of one of those common knowledge things that you need to know. It's a resource they listed. Okay, yeah, I would look into that for sure. I would definitely look into that. I'm not sure to answer your question. Is water reducing just when you are mixing the concrete and have a lower workability, or like when rain hits the concrete and rolls off? Oh gosh, Aiden, you are. Ooh, I don't know the answer to that. Isaac, can you help me out with that one?
Yeah. So I mean, concrete.
I think it's when you need a lower slump, right?
Yeah, there's admixtures you can throw into the concrete that make the concrete behave differently, and that's one of them. So water reducing admixtures can also be, I think they're also called plasticizers, and they all help to improve like the workability of the concrete. So
I would Google it just to double check us, but I think water reducing helps lower the slump. If you've got like a 6-inch slump and you need a 4-inch, you could probably throw in the water reducing, depending on specs. You know, RDOT up here in Arkansas has pretty strenuous specs, and they don't allow particular admixtures. I don't think they'll allow water reducing admixture in their concrete. So another question was, what is super plasticity used for? Joe, I don't.
super plasticizer, that's again
Yeah,
another admixture that you can throw in concrete. It's just a water reducer, and it also helps increase workability.
I'm making myself look like a fool pronouncing that wrong, but
It's all good. These are definitions, though. All of these little topics, these I guess definitions, are all really good to know for the PE exam, because this question could be flipped to ask what any one of those items are for
yep,
concrete.
it's good y'all are asking these.
So
Let's see. What was another one? The catch in this question is the word relief. You know, it could be. I think it's just understanding each of these and understanding what each of these do. I don't think that all of the rest necessarily increase pressure. I mean, we could really get the nitty gritty and think about the molecules and stuff like that. But I think it really boils down to understanding what each of these do and understanding the job that each of them do.
yeah, and I do think that's the key word: relief from internal pressure.
Oh, I see. I see what you're saying now. Yep.
You know, if you put all that together, you're thinking about which one of these relieves internal pressure. So,
My bad. Yep. You're right. All right. Any other questions? Good
oh,
stuff.
lots of good stuff in here. Excellent. Yeah.
Okay.
Question. Um, I don't know. We could read through some more of these. Andrew says water reducing admixtures, sometimes referred to as plasticizers, are designed to free trapped water present in concrete mixtures and are used in a variety of applications to ensure improved workability. Yeah, so a lot, a good question to deal with this kind of stuff is what can help improve workability. So think about um, how these questions, these theory questions, could be asked in different ways. I think it's very helpful to know what each one of these items is and what it does, because they could throw a question about any one of these on there. So, good point.
Joe
Boy,
had a
lots of
really good
questions on
Joe
this.
had a really good question. Would you ever use air entrainment and super, I'll let you say it, Isaac, together? I
The
presume
super
not.
plasticizer. Yeah. I I think a lot of these things could be added. Concrete's just like baking a cake, you can throw in all kinds of stuff in there to help improve its workability, improve its endurance when you have freeze thaw conditions. And it really just depends on what you're dealing with and the environment that you're placing your concrete in. A good question they could also throw out is if you're in a very corrosive soil, how to prevent that stuff. The code goes over how to categorize that, but there's probably a million questions you could ask on concrete. So it's just kind of helpful to understand the definitions that come up. We could probably ask 20 more theory questions on this.
Cool.
Good
Cool,
stuff.
cool.
Yes,
Yeah,
this one's definitely getting some attention. I like it.
all right. I need some more help. We're on a roll now. Everybody's warmed up. They got their typing fingers ready. Let's see. This next one is going to be a pavement evaluation problem, and this one should be a pretty easy one. If you're taking the FE or the PE, you really need to know this one. Oh shoot, I forgot to. Let me see here. Okay, there wasn't a reference for that last problem. I thought I'd forgotten to write it down. Here's what the question says: the 1993 AASHTO Guide for Design of Pavement Structures. By the way, if you're taking the PE, it literally gave you the standard to look in. So that they can do that sometimes, by the way, for the PE problems. It defines a cumulative expected equivalent single axle load, or an ESAL, to be how many kips. All right. So everybody time in, or chime in, not time in. Which answer you think it is. It should be something that you kind of remember from school. We're going to have an ESAL problem on deck. I mean, it is on deck, baby. We're going to be working through a good ESAL problem, but this is just a little primer. Just get everybody warmed up. And I'll give you another hint. In this guy right here, this standard, you're going to look on page I-10, I think is what it is. Section 1.4.1. So if you want to go find it, or if you're taking the PE reference handbook, I said it could be an FE. So the PE, typically with the PE, you're going to be taking a little bit of time outside of school, and you're not going to remember this outside of school, right? And so they provide a lot of the definitions for an ECE reference handbook. It's not in the FE reference handbook. Doesn't mean that it won't be on the FE exam. Does that make sense? Like, some of it can be common sense that you need to remember from school. So this is, we need to look in version 1.2, and you can find some details about ESALs on page 297. We have a ton of people chiming in with B. Good job, everybody. Awesome, awesome, awesome. Yep, it is B. It's 18 kips. That is a ESAL, 18 kips. So good job. Any questions? We got a banger of a problem on deck. I'm excited for it.
No questions. Just a lot of comments on B. Motorhead 1 says 26 kips on modern trucks. FYI.
All right. Here's our big daddy right here. This is going out with a bang, our last problem of today, and then you can go back to your football. I know it's a letdown that you have to go back to football, but this is this is good stuff. So here's your FE. Let me make sure I have an FE standard for it. Yep, I do. This is an FE or a PE problem. We're going to be talking about pavement evaluation again. This is an ESAL problem. Here's what the question says. A 4-lane road, so 2 in each direction, has a AADT. That is the average annual daily traffic. So basically it's 1 year of data, and they divide it by 365 days. So 17,400 vehicles go through this sort of study every day. With a directional distribution factor of 0.52 and the following truck classifications and percentages. Assuming an average annual growth rate of 2.7% for all vehicles over a 20-year design period, determine the ESALs to the nearest million for the design lane. Okay. Talk about a mouthful. We're given a chart with truck classification, so passenger cars, panel pickup trucks, 3-axle tractors, semi-trailers, percent of AADT, and an axle load equivalency factor for each of those truck classifications. So basically what this sort of table is giving us is 65% of the AADT is going to be passenger cars. 20% is going to be panel pickup trucks. 15% is going to be 3-axle tractor semi-trailers. Okay, so that's where that comes from. Now, whenever we are looking for some reference material, looks like I totally forgot to stretch this problem out to cover the, just pretend that looks better. Typically, I'll move the problem statement out to where it covers the whole screen. But anyways, let's see. So if we're looking for some reading material, the FE reference handbook, the latest and greatest is going to be version 10.2. And we're going to be looking at page 308 for this guy. And they're going to have to provide you a lot in the problem. That includes, let's see, well, they're just going to have to include you a lot. So I wanted this to pertain to the FE and the PE exam takers as well. So both of them. So I kind of left a little bit of material out, but go ahead. If you're taking the FE, you're not going to have to remember some stupid long equation and it not be provided on the handbook. So make sure that you are looking in the reference handbook, understanding what they give you, and comparing it with this problem, because they're going to have to provide you with a lot of material for it to be applicable to the FE. But in order for me to apply this to the PE takers as well, I had to leave a little bit of material out, but I'm going to provide that later on later through this problem. So just recognize what you need to be given in order to solve this if you're taking the FE. Now for the PE reference handbook takers, we're going to be looking in version 1.2 at the time of this video. I forgot the V right there. Or page, let's see, 278/297. We're going to find some good deets right there, good detail in those guys. And you can also look in the AASHTO Guide of Design Pavement Structures, the 1993 version that I was telling you just a while ago. You can look in that. That's going to be Appendix D. So I'm just going to write AASHTO. Let's see if I remember how to spell it. AASHTO. It's going to be it's going to be the Guide for Design of Pavement Structures, 1993. I'm just going to write Appendix D. And Table D20 provides you with some stuff that we're going to need. Table D20. All right. It's going to provide you with traffic growth factors for 2, 4, 5, 6, 7, 8, and 10%. So notice in our problem, we're given 2.7%, not 2, whatever it was, 2, 4, 5, 6, yada, yada. We need to use the equations they provide on table D20. So whenever you're taking the PE, the biggest way, the most important way to solve a problem is understanding where to look in the reference, understanding which reference to look into, right? And so in this case, understanding that we're talking about ESALs, we need to go straight to either the PE reference handbook or the Guide for Design of Pavement Structures, 1993 version. So they'll provide you all this stuff on the exam, or not on the, they'll provide the references for you for the exam. You'll just have to go find where it is in each reference. So just keep that in the back of your head. You need to know where to find it. All right. So step number 1 is going to be converting the AADTs into, vehicles per truck classification. So we're given a total average annual daily traffic we're given a total number for that. We need to go ahead and split that up between passenger cars, panel pickup trucks, and 3-axle tractor semi-trailers. All right. So what we're going to do is we're going to multiply the average annual daily traffic, tongue twister, man. We're going to multiply that by 65%, 20%, and 15% to give our vehicles for each truck classification. So I'm going to go ahead and write that out. I'm going to abbreviate passenger cars to PC just to, be lazy. Pickup truck is PT, again, lazy. And then I'm going to write 3-axle right here for our 3-axle tractor semi-trailers. All right. So what we need to do is I'm going to draw a colon here. We need to take that 17,400 and multiply it by 65%, 0.65. Same thing with these guys, 17,400 times 20, so 0.2. Same thing with this dude, 17,400 times 0.15. All right, we're going to set those equal there. And whenever you do the math on these guys, by the way, I encourage you to get your calculator out, solve this with me. It helps ingrain things in your brain. Whenever you pull out your calculator, you're getting the right answer. You're getting the same answers. And if you get something wrong, let's talk about it. Let's get it. Let's dial it in. So we end up with 11,300 here. 310. Ooh, about messed up right there. I talked about me messing up. There we go. This guy's going to be 3480. All right. And then this guy is 2610. I keep hitting the erase button. So now what we need to do is convert that to a yearly. So what we just did was we took the average annual daily traffic. Remember, it helps to understand what that means. That is 1 year's worth of data divided by 365. So that's where you're getting your average annual daily traffic. So they took an annual amount of data and then shrunk it down to a daily data. So they divided it by 365 days in a year, got daily data. So average annual daily traffic. Now notice we have daily data. We need to multiply that into yearly, because what we're going to do is we're going to take the yearly traffic data and we're going to forecast it 20 years with a 2.7% growth rate, plus a directional distribution factor and another factor that we're going to talk about a little bit later. All right. So we need to convert this over to yearly, because if you end up converting the daily, you're just going to get a completely wrong answer. So what we need to do is we need to multiply this to 365. So now we are solving for the number of vehicles, that being the passenger cars, the panel pickup trucks, the 3-axle tractor semi-trailers. We're taking each of those and we're now solving for a year's worth of data. So we're trying to find how many passenger cars went through this study area in a year. Okay. All right. So this guy is going to be, let's see, we'll go ahead and do this. This is going to be a lot, by the way. These are going to be pretty big numbers. 41281. I see somebody's already got an answer. I don't know. Let me see if you're right. Okay. We'll come back to it. 4128150. I think that's our guy. And then we have 1270200. And then we have 952. Let's see, 650. Everybody get that? Everybody get the same stuff? All right. Step 2 is going to be forecasting to the future traffic demand. So by doing that, we need to get a growth factor. There's something called a growth factor. It's G, and you'll find it in the PE reference handbook. I think it's 278, I think, is where you'll find that. Maybe I can't remember which. No. Sorry, G is actually in the it's in the ASHTO book. Man, I had a brain fart. We need to solve for G. So this G right here is your growth factor. This guy is essentially, you'll remember this from engineering economics. It's 1 plus G, lowercase g, by the way, raised to the n minus 1. We're going to put that over our lowercase g. Now this right here, I just said you might remember it from economics. It looks a lot like the F given A from engineering economics. I know a lot of people have pain PTSD, if you will, from engineering economics. I did. I think I had to take it twice. Maybe I took it once, but it was such a long class that I hated every bit of it, and it felt like I took it twice. Maybe I did. I don't know. But F given A is as follows. So you're solving for F given the A. That's what that stands for. If you're kind of lost right now, I encourage you to go check out some of the engineering economics problems on YouTube under Civil Engineering Academy. We have some pretty good practice problems there. So this is equal to A times 1 plus I. Raise that to the N. So this is just familiar territory. It's nothing to do with the problem. It's just so I can show you the link between the two. It's essentially the same thing, right? So we're solving for a final growth factor, except we just don't have this A, right? So that's the similarity between the two equations there. So if we're going to solve for this guy, it ends up looking like this. We have 1 plus, man, I keep hitting that erase button, 1 plus 0.027. So that's 2.7%. We're going to raise that over a 20-year design period. And sorry, I totally forgot to go over the unknowns. I'll explain that here in a minute. 0.027. And this is going to be minus 1. I almost forgot that. That's on the numerator. So the big G is the growth factor that I was telling you about. The little g is the annual growth rate. So that's 2.7%. We need to make sure we put that in decimal. Don't put it in the percentage. You'll get the answer wrong. So make sure you put it in decimal form. And then the N is the number of years that you're trying to forecast. So that's 20 years for us for this problem. And so when you solve for this, you end up with a growth factor that's like 26. Let's see, 26.065 is going to be our growth factor. So what we can do is we can multiply each of our traffic volumes by this growth factor, and then we're solving for a forecasted traffic count, forecasted traffic analysis. I'm trying to think of wordage there. So we're basically forecasting it, right? We're forecasting it 20 years into the future by multiplying it by this growth factor. And that will give us our design ESAL, or our design traffic, our design number of vehicles. That's what we're going to use to solve for our ESALs. So I'm going to go ahead and scroll down just a little bit. What we're going to do is we're going to take the passenger cars, the panel trucks, pickup trucks, whatever you want to call them, PTs, and the 3 axles. We need to make sure we multiply these guys by the growth factor. So that's what I'm going to do next. I'm going to take, let's see, 412 8150. The passenger truck or the pickup truck was 1270200. Yep, that matches. And this guy's 952650. Everybody still on board? Everybody still awake? We're going to multiply this by the growth factor, 26.065. Same thing with this dude. So basically, remember what we did was we took the the average annual daily traffic, and we split it up between the different truck classifications, multiplied it by 365 to get us to a yearly quantity. And now we're forecasting that yearly quantity based off the growth factor and the number of years that we want it to grow, or that we're designing this pavement for. Okay, so that's what we're at now. We are forecasting it with that growth factor. It's 26.065. Okay, this guy's equal to that. That's equal to that. Okay, so now we're getting in some really, really big numbers. Like I said earlier, that's kind of why it's taking me so long to write these down, is I got to make sure I write them down right. This is going to be 107,600,229.8. And by the way, I want to say something real quick. The PE, if you're taking the PE or the FE, sometimes, they don't make the exam to be really realistic. What's the chances of 107 million cars, 108, we'll round up, million cars going through this stretch of road, a 4 road? I mean, it's not, probably not going to happen. They're going to upgrade the road or something like that. So if you end up with a big number, but you're following the steps correctly, don't be alarmed. Just pay attention to your steps. Make sure you're doing it right. Make sure you check your units. sometimes they can have some unrealistic numbers with the exams. All right, so this next one's going to be 33, 107, 763. Almost forgot how to write a 6 right there. This guy is going to be 24, 830, 822.25. All right, and I'm going to go ahead and round these guys up because you can't really have a 0.8 of a vehicle. You can't have a 0.25 of a vehicle. So with this next calculation, I'm going to round up to the next vehicle. So I'm going to say that there's 107,600,230 vehicles or passenger cars going through this study area in 20 years. All right, so just a heads up on that. I'm going to round up those two. All right, don't worry, guys. We're almost done. Okay, I know you're having a lot of fun, but don't worry, we're almost done here. So now what we need to do is we need to multiply our design traffic times our ESAL factors. Remember, our ESAL factors is given to us. It's given to us right. Oops, I accidentally wrote there. Right here. That's what we're given. So we're going to multiply our design traffic that we just solved for. So we took a yearly quantity of vehicles, we forecasted it by 2.7% over a 20-year design period. Now we have our design traffic or our forecasted traffic counts every single year based on the particular vehicle, right? We multiply that by our axle load equivalency factor, 0.00. How many zeros was that? 0.08. So I think that was 3 zeros. 0.0122 and 0.8646 respectively. We multiply those by the particular traffic classification design traffic, right? Multiply that, and we end up with a number of ESALs. We're getting there. We're so warmed up. We're getting there. All right, so we're down, and we're going to do that. So for passenger cars, let me start another row here. Passenger cars, we got panel trucks / pickup trucks. We've got 3 axle. And we're going to go ahead and write this out. I'm running out of time. Okay, we have 107,600,000, 230, and then we have 33. Let's see, 107, 763, and then 24, 830, 823. Now we need to multiply it by our ESAL factor. So for passenger cars, it was 0.0008. This guy right here was 0.0122. This guy right here is going to be 0.8646. And this ends up being equal to, let's see, here's our number of ESALs. Get ready, everybody. 86080.184. The next one's going to be 43914.709. And the next one's going to be 214687. 29. Let me make sure. 2957. 29.57. All right. So now the next step is we need to add all of these ESALs up. So the reason why is because we just ESALs given or for each traffic or for each truck classification. Now we need to add all of these ESALs up in order to multiply it by our directional factor and our lane factor that we need to get a hold of. We can I'll tell you where to find each of those. I think the directional factor was given to us in the problem. The other one we can find in the PE reference handbook. So then that was part of the reason why I was saying earlier, if you're taking the FE, they're going to have to give you some stuff. The lane directional factor would have been one of them. Okay. So whenever we add these guys up, you end up with 21958,724 ESALs. But we're not done. We're not done yet. We got to multiply it by our, since we're solving for the design lane. Remember, it says for the design lane. That's the very last end of the problem. That's where you can get it wrong. We need to solve for the design lane. We need to multiply this by the formula that we find in the PE reference handbook, that being the ESAL. Dang it, I use sigma. ESAL design lane is equal to the directional factor times the I think it's the lane factor, lane directional factor, something like that, times ESAL. So our total ESAL that we just solved for. And so what we need to do is, let's see. So D was given to us in the problem. It's 0.52. I'll show you where I got that. Right there. So that's our directional distribution factor. Let me scroll down. Our DL we can find in the PE reference handbook. So this is going to be page 278. So I'm going to write PE reference handbook. I apologize that we're over on time, everybody. I really do. I thought I had more time than I did. This is page 278. And so what you have to do to get your answer is you have to understand there's 2 lanes in each direction, which means there's 80 to 100% ESALs in our design lane. And so our factor here, given those quantities, remember it said 2 lanes in each direction in the problem statement, our DL is going to be 0.9. Okay, that is expressed as a ratio. So if it's not provided, you'll have to interpolate. All right, let's see here. So now I'm going to scroll down and we're going to go ahead and plug and chug. So ESAL in the design lane is equal to DD, which is 0.52. We're almost done. We're almost done. Times that 0.9. And then we multiply that by our ESALs. Remember, we added all the ESALs up for the passenger car, the pickup truck, and the 3-axle. It's going to be 21,958, 724 ESALs. All right, let me see if I rounded right there. No, I didn't. All right. And so finally, whenever we add this guy up, ESAL in the design lane is going to be equal to 10,276, 682.83 ESALs. All right. This guy's going to be, let's see, to the nearest million, it's going to be A. Everybody good on that? Any questions? I apologize that I went over in time. I'm going to hang out. If you need to go, that's fine. But yeah, the answer for this one's going to be A.
That one put him to sleep, Cody.
Yeah, I believe it. I told you it was exciting. I told you I was trying to hype everybody up before it. That way I didn't have anybody falling asleep, and it looks like it happened.
There is a question that popped up. Why, as my semi truck has 2 axles and rear, allowed 42 kips? Was that part of the problem?
Yeah, I'm not sure.
Where is that coming from, I guess? Maybe a little more detail on that one, Motorhead. Good question, though. Yes, thank you. Got the same
You're welcome.
calips. Looks right. Thank you. It was great. Got the same answer.
Good.
Awesome. Way to follow along. You know, practicing problems takes time, but
JS, it could be. They would have to give you the material that you find in the AASHTO, the Appendix D, the table D20. Obviously, you're not given that one. But they could make it a lot more simpler and make it a breadth problem. They could give you a lot of stuff and just make you use that formula that you find in the PE reference handbook. Anything that's in the reference handbook is free game for the breadth. So heads up on that. I mean, if you aren't studying any of the transportation stuff in the PE reference handbook, I would definitely take a look into that and see what all is in there, like horizontal alignment or horizontal curve, vertical curve, that type of stuff. But as far as diving into the references like the AASHTO book and stuff like that, you won't have to do that for the breadth. Does that answer your question?
yes.
Good.
Awesome. Well, let's go ahead and wrap this up. We'll just turn our screens on real quick. Cody, thanks for jumping on and doing this one for us. It's always nice to have people that are, on the verge of taking the exam come and jump on and do this stuff. So I appreciate you doing that.
I appreciate everybody's involvement. That was a lot of fun.
Yeah, it's fun to see the chat room active. Getting comments. This is definitely a transportation depth question. Yes. Well, good deal. Thanks for joining us today. We're going to keep this live on our channels for some time. Eventually, these do come down. We do archive them into our courses, so you'll want to check them out there. If you are not a member of our course, go check it out at civilengineeringacademy.com. And again, if you have any questions that you want to do another live problem-solving session for some reason, We always try to hold these frequently. Get us your questions, and we will get them in our queue to do. So thanks, everyone, for joining, and we'll see you on the next one. Thanks, Cody.
See ya.
Okay, bye.
Good luck, everybody.